right, so first off, we've done divergence, right? We've done it for 2D vector fields and we've done it for 3D vector fields. Divergence actually is one of the easiest things we ended up calculating probably all semester because it was just summing up the partials. So remember what divergence gives us. So this is going to be, let's do a little recap of what divergence gives us. And I think that'll help it make sense in the larger context of how it applies. So remember that we talked about divergence being a source or a sink. It was a source if it was an outward moving divergence, a sink if it was an attractive force. Gravity, for instance, would be a sink. A gas expanding would be a source from a single point. So every individual point has its own divergence in a vector field, just like it has its own curl. Curl was circulation, divergence was expansion or contraction. So basically it's this outward, it's an outward flux. It's an outward flux density. So it's designed to work for a flux integral because all we need to do is sum up all the divergence in a region. So the example we gave before is air is heated, right, at a single point, it expands in all directions. So we would have a positive divergence. You know, if we had an attractive force, it's all being sucked towards this particular point. So again, this is all repeated information, but we've talked about divergence a couple times at this point. I think you got an intuitive understanding of what's going on, right? If it's positive, it's a source and it's moving away. If it's negative, it's a sink and it's moving towards. And we looked at it in 2D with CalcPlot 3D a little bit. So why do we care about it again now? Well, and we looked at these plots before too. Because we just did flux integrals. And if you think about when we did them in 3D, one of the last problems we did going through a surface, right? So we need to think about that in terms of divergence. Now, again, to calculate it, super easy. If you're given a vector field, the 2D divergence is the sum of the partials. And it is straightforward. The first part, the first component is dx, second component dy. If it's a 3D, third component is dz. Now we're specifically going to be interested in 3D in this case, okay? Because we're looking at surface integrals and we're looking at 3D vector fields. So here's the idea behind the divergence theorem, although I think I've already kind of talked about it. Imagine pumping air into a container, right? The air in the container is going to compress and will eventually leak out or somehow get through that surface. If we think of it representing a fluid, right? Then then F represents the expansion, excuse me, the divergence of F represents the expansion or contraction of that fluid. Now, if we try and put that into a container or some sort of closed surface, well, eventually that fluid is going to start to go through the sides. Again, assuming the container doesn't just explode, right? Because that's what flux is. It's a measurement of how much of this, whatever it is, gas, fluid, magnetism is going through a surface. So basically the divergence theorem kind of combines these two ideas. It combines the surface integral, the flux integral that we were talking about on Tuesday, with this idea of divergence and says, hey, basically, when we're looking at the total divergence through a surface, we're looking at the total flux. So by summing up the divergence within a closed surface, we're actually finding the total flux. We have the capabilities of doing that because we have triple integrals. So the divergence theorem allows us to use a triple integral in order to do a surface integral. Now, one of the things that is necessary is we do have to have a closed region. If it's not closed, we need to make it closed. But depending on our region, this can be very easy to do because number one, again, I think divergence is one of the easiest things we find all semester now that we're really good with partials. So finding the integrand's not a problem. The only other thing we have to do then is set up the triple integral, which we had plenty of practice back in the last module. So again, mechanically, nothing new. Divergence we've done before, triple integrals we've done before. Conceptually, okay, we had to make this tie between doing a triple integral of the divergence and a flux integral. So it's kind of similar to Green's theorem. Remember, Green's theorem required our path to be a closed loop, so the region was enclosed. Same idea here. Divergence theorem expects the surface to be a closed 3D surface. If it's not closed, you need to make it closed and then remove the part that any contribution from the part you added in. So, like Green's theorem, we can't use it, just like with Green's theorem, which we can't use for all line integrals, we can't use divergence theorem for all surface integrals. But if we have a closed region, we want to see if divergence theorem makes sense because, again, the divergence is so easy to find and we know how to set up the limits for a triple integral. So we did this one last time. We have a 3D region. We'll assume an outward orientation like we did last time. I believe the answer came out to be 11 pi over 6. Actually, I'm gonna have it on the slide. So there. This one I actually wrote down so we didn't have to remember. All right, let's talk about setting this thing up. So again, we're using two things that we have done before. Number one is the divergence of F. So the vector field. Okay, well, that's going to be d dx of x plus, and you guys obviously don't have to write this up. I'm just reminding you of it. d dy of y plus d dz of z squared. So what are we going to have? 1 plus 1 plus 2z. So 2 plus 2z. That's our integrand. We're done with the integrand. The only thing we have left now is to come up with what the limits would be for a hemisphere. If that seemed easy, it's because it is easy. There was no trick there, right? We talked about that before. Even way back when we did divergence back in the last module, we were like, oh, this is easy. It is. Divergence is easy to compute, but it's very powerful. It's kind of like the gradient. Well, no, the gradient's more powerful, but it's kind of like the gradient in that, wow, we can do a lot with just a little bit of effort. Okay, so now we need the bounds for a hemisphere. Because it's a hemisphere, let's do z first. So dz to square root of 1 minus x squared minus y squared. And now we're just left with a circle of radius 1 in the xy plane, which again, we've done how many times at this point, right? Negative square root of 1 minus x squared to square root of 1 minus x squared. Negative 1 to 1. There it is. That's our triple integral. Now, we're not going to want to do that by hand. Probably we would change this into either spherical or cylindrical coordinates. Kind of your preference. Spherical might be the easiest because all your limits would be nice constants. You have to transform the z and add in your rho squared sine phi. But we could do it in any of them. But even this, let's see. I don't know if I have this one in there or not, but let's take a look. No, I converted it into cylindrical. I took the easy way out. But there's our divergence, and there's our integral, 11 pi over 6. I did it in cylindrical. I think probably Symbolab could do that one in rectangular, but if you run into any issues on it, we know how to convert it into something easier. Again, spherical probably would be the easiest if you had to do it by hand, but cylindrical I don't think would be too much of an issue for for Symbolab. And that's the divergence theorem. Like I said, it's a short section. There's really not much else for me to say about it. You know, you'll know whether or not you can use it because you'll be looking at a closed surface. And you'll say, hey, I know how to set up this closed surface in 3D. I've done something like this before, whether it's, you know, a plane bound by a circle, or you know, think of all the shapes that we did. Any of those now, we could actually go back and say, hey, give me a vector field for that, because now all we need is the divergence of that vector field and put it into that triple integral, and we can get the flux. So again, what's nice about Stokes and divergence theorem is mechanically we had nothing new, right? Stokes theorem, we did surface integrals. Well, we did that last week. Divergence theorem is just triple integrals. We haven't done those in a few weeks, but we've done them. And this will be good. It'll give you some practice going into the end of the semester. So mechanically, there was nothing new today. Conceptually, yeah. Okay, how do we use Stokes theorem? What are the criteria that allows us to use it? Okay, great. Well, now we know what that is. Same thing with divergence theorem. When are we allowed to use it? And what is it giving us? Oh, okay, it's giving us the total flux. So again, Stokes theorem is a surface integral that we used, a surface integral over a vector field that we used to get a line integral, right? The divergence theorem is a triple integral over the divergence that we use in order to get a flux integral.